So let's get started. So welcome back from break, everyone. So I'm hoping you had some time to have some time to enjoy yourself, sort of break, but also to work a little bit on the project, and you're able to get some stuff done towards the towards the intermediate report. So the second half of the lecture today, we will, so around 3:40 or so, I'll stop the lecture where I'm up here talking and doing stuff, and we'll break into groups, and your groups will give peer feedback to each other. And then as of this morning, all except 3 groups had signed up to in one of the slots to meet with me, either after class today, after class Wednesday, or some time slots we have on Tuesday. I believe if your group did not sign up, then Sunipa should have sent you an email, I think, through Canvas to tell you to sign up. If you haven't done that yet, you should do that. If you can't make one of the times, let us know. We'll figure out another time to make work or do it over Skype. So the homework 5 for regression is out. It was out right before break. You don't have all the, we haven't gone through all the material yet to do the homework, so we'll do that. I might be open to moving the deadline back to this a little bit, but let's see how it goes. I don't want it to run into the final report deadline here. So the other thing I've gotten questions about is, again, I moved around the order of a few of these lectures. The 2 regression lectures after break, I think, are ordered 18 and 19, and this one is 17, and the one tomorrow or Wednesday is going to be 17. I kept the numbering, but I changed the order. So sorry for the confusion about that. So today we're going to have lecture 16, and this is going to be about this technique called random projections. And this is another approach for dimensionality reduction. Okay, so that's when you have some large data set with many attributes. And it has many dimensions for each item you have in the data set, and you somehow want to kind of reduce this to having a smaller number of pertinent attributes so you can work with them. Those are the groups. So we're going to start with we're going to have so start with the data set, and I'll call it A, And you can think of it as being A1, A2, up to AN. So we have N of these data points, and each of the AIs is going to be in RD. Okay, and I think for reasons that it corresponds with the literature a bit better, in the notes, I write this as A is going to be in D cross N, so that you can think of this as a matrix. So it has D rows and N of the columns. And so we're going to reduce the number of rows. This is just the way it tends to show up. I think with the lecture today, I think this is more normal to how we normally do it. I'll keep it as each of the vectors is a row vector. And then at some point, I'll do something that's the transpose of what generally shows up in the literature. What the goal is here is to map A, this data set, into another data set B. So B is now going to be in, this data set is going to be in RD prime, where D prime is much less than D. Okay, so now I still have N data points. I still have N data points like I did before, but they're in a much smaller dimensional space. Okay? And I want to do this so it somehow preserves properties of the original data set, right? So we talked about one way how to do this already. So what was the one where we talked about how to do this?
Multi-dimensional.
What?
Scaling.
So multidimensional scaling is close. Multidimensional scaling takes input as a distance matrix. So it has all the distances between all pairs of points. And then it produces, again, points in a low-dimensional space B that try to represent those distances. And this will end up being somehow closer to, in some ways, it'll be similar to what we're doing here as well. But the setting is just a point set that's in high dimensions. How do we reduce the dimension of a point set? Yeah?
SVD and then ring K approximation?
Yeah, so we can do SVD or we can do PCA, which is just centering first, but something like the SVD, right? So, so the previous approach was PCA, and what this did is it found essentially the best rank K approximation of A, and so it did this by using the singular value decomposition. And what this did is it writes it writes A as the product of three matrices U, S, and V transpose. And V transpose has the singular vectors inside of it. It sorts them based on orders of importance. These are orthogonal, and you project onto the top k dimensions of V, the top k dimensions of those, and it gives you, in some sense, the best way to do this dimensionality reduction. Okay, so basically, these are the let's write this out. The right singular vectors are V. That this is a set V1, V2, V3, Vk up to Vd, and so these give me a new basis. These are all orthogonal to each other. And so I can get a new lower dimension, a new k-dimensional subspace for each of the points of A. I can project to get Bi is going to be the dot product of V1 with AI dot product of V2, AI up to dot product of VK equals AI. And so this gives me a k-dimensional vector. I take the first k of these right singular vectors, and I project by doing just a dot product of each of the data points onto each of these, and this gives me k different coordinates here. And these k coordinates gives me a point that's in, this point is in RK, right? So this is a lower dimensional subspace, right? So and this gives me a new point BI, which is k-dimensional. And in some sense, so I'm preserving properties of A by projecting down into this lower dimensional subspace defined in this way. Okay, and I said this was optimal. So why are we saying something else that this was optimal? It was optimal in the sense that it was this minimized the sum equals I equals 1 to n of, say, the distance from, this is AI minus BI squared. This was one of the things that this minimized, this approach. If I were going to get a set of k-dimensional points, actually not defined this way, if you define them, okay, I have to define it slightly. I can't directly compare this because this is k-dimensions. I can show a k-dimensional representation of this in d-dimensional space. So I can say instead that projection onto VK, I'll skip the details of how to describe this, where BI is basically, this is a representation in d dimensions, this is a representation in k, but then it minimizes the sum of these squared areas. All right, and so this was optimal in this sense. And that if I want to minimize the sum of the squared distances of this projection, then this was the best way of doing it. Okay, so actually over the next 2 lectures, we're going to talk about 3 different ways that somehow improve upon PCA. Now they don't improve upon it in terms of minimizing this. And so typically, if you really want to get the best representation in lower dimensions, like getting down to 2 or 3 dimensions, then this is really going to be the best way to do it if you're kind of trying to worry about the overall error. Okay, so we're going to talk about something on Wednesday that's going to be more efficient and can work over streaming data. Also on Wednesday, we're going to deal with something where these new coordinates are not as interpretable as the original coordinates, because those may have corresponded with actual times, like actual attributes that you could say, okay, this means this was the reading on the jth day of a series of days or something like that. So these aren't necessarily interpretable, so we'll talk about ways to make these more interpretable on Wednesday. Today what we're going to talk about is kind of probably the coolest of these approaches, in that instead of minimizing the overall error, it's going to say I want the error on all of the data points to be small, not just essentially the average of the error. This might have one of the data points to have a lot of error, while the other ones have a small amount of error. Okay, and it won't quite phrase it, so it doesn't phrase it in this way. It changes what is being optimized here. The other thing about this approach is this PCA or SVD approach needs to do some sort of operation here in order to do this singular value decomposition, which, as we'll again discuss on Wednesday, it can be kind of slow on large data. And it can take up too much space on your computer on large data. But it also needs to essentially look at all the data before it decides how to do this. We're going to talk about a way that's going to be oblivious to the data. It decides how to project to a low dimensional space, but it also needs to essentially look at all the data before it decides how to do this. We're going to talk about a way that's going to be oblivious to the data. It decides how to project to a low dimensional space, without looking at the data. So it's kind of magical in that sense. Okay. So what we're going to do instead is, I'll call this the Jael Objective, and I'll explain where this name comes from a little bit later. But what this is going to try and satisfy is, I want to say, for all pairs, and I'll call them A and A prime in A. So I have this data set, which again lies in RD. Then I want to find a linear mapping, which is going to go from RD to RK. So we're going to say property, let's see, if I want to look at this distance between A and A prime, and this is just going to be this straight line Euclidean distance. So this is the original distance. I want to say that if I shrink this by a little bit, that this will always be less than the mapped distance, and it will not be, and the mapped distance will also not be too much greater than the original distance. Okay, so this is, so A minus A prime is the original distance in the high dimensional space, right? And this is going to be the new distance in only k-dimensional space. So I'm going to go down to some much smaller dimensional space, and preserve that for all pairs of points that the distance is approximately the same. There's some epsilon parameter, and so say for air parameter epsilon. And so epsilon will have to be between, say, 0 and 1/2. Typically, epsilon equals, think of it as, say, 1/10 or 1 out of 100. Right? So say this would be 10% error or 1% error in the distances. Right? So if the distance is really big, right? If the distance is, from starts out as 20, right? Let's say the original distance is 20, and so let's say that's one of the larger distances. Then, and I have 10% error, then I know the new distance will be between, and error is 10%, so it's going to be between, it's going to be between 22 on this side, and this one is going to be an 18. Right? So if I get 10% error, then my projected distance will be between, say, it's going to be in between 18 and 20. If the original distance was 18 and 22, the original distance was 20. Let's say epsilon equals 1/10, and A prime equals 20. Then I know that mu of A minus mu of A prime, this is going to be in the range between 18 and 22. Right, so it's going to be in this range, which is going to be pretty close. Right, if I set epsilon to be equal to 1 out of 100, then this is going to be between 19.8 and 20.2. Right, so it's going to be much smaller error if I do that. Right, but this still seems fairly reasonable. Right? Okay, and this should hold for all points. Whereas PCA, I didn't have that guarantee about all points being true. Now I have this true for all of the points. Okay, and so if a point is smaller, right, if the distance is only 2, then this is going to be between 1.8 and 2.2. So it has a much, the amount of error I get shrinks with the scale of the distances. So if the distances start large, they stay large, and my error can be larger. If they start small, they stay small, and the error is essentially the additive error is smaller as well. Right? So it kind of adjusts it. So like if I have points which are clustered together, the points in the cluster stay in the clusters as I do this projection. Where that might not be true with PCA. Now if you're doing a k-means objective function, right, then you care about the sum of the square distances, and so then if a few of the points change, it may not be a big deal. But this in fact guarantees all the points are roughly the same distance as they were before. Okay? And so the cool thing about this is that the size of k, so the number of the dimensions k needed is going to be big O. There are some constant factors which aren't too big. There may be 1 or 2 in here. 1 over epsilon squared times log of n over delta. So this holds with probability at least 1 minus delta. Right? So there's a delta probability of failure. Think of setting this down to be something like it's inside of a log, so I can set it to be 1% probability of failure. It's 1 over epsilon squared, right? So if it's 1/10, then this becomes roughly 100. And then log of n, right? So log of the number of points. This does not depend on the original dimension of the data. It doesn't matter how large the original dimension of the data was. I can always project down to roughly this many dimensions and get this error guarantee up here. Yeah.
And so we will take like the floor or the ceiling of that number?
So this is it's a big O notation. So I'm hiding things like ceilings and floors, and the base of the log and various other stuff. So n is typically going to be a large number, right? Probably n is going to be much larger than 1 over delta, right? So there's some stuff going on in there. Yeah, so what's kind of amazing about this is it doesn't depend on the dimension of the original data at all, and I can always get this guarantee. So what's kind of saying that if I have n data points, they're really only log n roughly dimensions which really matter. There's some set of log n dimensions which capture just about everything that's going on. And how much you want to capture going on, well, that changes with your epsilon error parameter. The more, if you want to capture every single nuance about the distances, then you need to crank up this part in front here. If you don't care so much about that, let's say you wanted to get, instead of 10% error, let's say like 50% error, then this is like a factor 4 in front here. Right? But that still would capture the big picture of the distances. Right? You can, so really this log n thing is kind of to capture all the distances. And so this is a randomized algorithm. It turns out this n is only because I capture all the distances. If I want to capture only, I say, I want to do this and I'm only going to check one pair of distances. I don't know which one it's going to be ahead of time. Then I can get rid of this n. If I only need to check one of the pairs of distances. So you can even, this is for checking all the distances. It comes from a union bound in the analysis. Okay. So this is different from, and this mu mapping, this mapping mu goes to d to k dimensions, it does not need to know what the data is. I can define this ahead of time. I define it through a random process. Once I define it, it's fixed. Right? It does not need to know what the data is, like doing SVD and PCA that needed to know very intimately the structure of the data. Right? It creates the mapping before it sees the data. right? So that can be useful in case I need to define what this is before I'm about to get a bunch of data. I'm going to need to process it really quickly. So, I need to define this ahead of time. Okay. So, and so this was called a Jael Objective because this comes from a theorem from Johnson and Lindenstrass. And I think this was 1985. And it was actually not even a theorem. It was a lemma inside of a really long paper they had. I think it was like a 2 or 3 page proof, so it was still a substantial thing. But this was kind of a side objective of what they were trying to understand. Turns out people have worked on it, and the proof is now much simpler. I think I proved it in like this one of the hidden kind of lectures, one of the hidden lectures in the first thing. It takes about a page, and I think you could understand it. I think I referenced it. It's in the. I didn't explicitly cover it in class, but it's linked off, I think, the first lecture line in the class notes. Okay, so how do we actually do this? All right, so how would we create this mapping? All right, so anyone have any? So who's heard of the Johnson-Lindenstrass lemma before? This is new? Okay, so anyone guess of how to make these mappings?
Some kind of optimization process?
An optimization process people have tried stuff like this. It turns out it's kind of hard to do that, and that would require looking at the data. If you remember the title of the lecture, random projections, right? So we're going to do some random projections. So okay, so I'm going to define a set of k random projections, right? We're going to call each one mu I, and this is going to go from RD to RK, and then it's going to turn out that mu of A is going to be mu1 of A, mu2 of A, and so forth, right? So I'm going to create one, and each of them is going to give me one dimension of the new space. And how do I create a random projection? So do you remember what a projection is? Yeah.
So you generate a random vector using, like, doing, I think we did Gaussian random variable. That way I think it's approximately a directional unit vector.
Yeah, that's right. So each one of these is going to be a projection with a random vector, and we want it typically to be so it's a unit vector, but we can just actually use random Gaussians, right? So what we're going to do. So how do we create a random vector? So we're going to start. In order to do this, we need to create. We're going to create UI, which is going to be a d-dimensional normal distribution, basically. So is going to be like a d-dimensional Gaussian. Okay, so we can start with so it has a mean of 0 and a standard deviation of 1, so it's like the identity matrix, right? If you remember, I mentioned in one of the locality sensitive hashing lectures, how do I do it? You can start with d random, uniform random vectors between 0, 1, we can do this. We can do and there's this thing called a box Mueller Transport, where I take in D vectors that are each in between 0 and 1. They are uniform between 0 and 1. I do this box Mueller transform, and I get a d-dimensional Gaussian random variable. Where I do d over 2 of these box Mueller transforms. Right? And so I can get a d-dimensional Gaussian random variable. And if I'm not sure about if I've normalized it correctly, just to be totally clear, I can re-normalize it a bit. Let me call this VI just to distinguish it. And as I'm going to make it so it's normalized. This is a U. Right, so I've taken this vector, which is a random Gaussian. That means that any direction I point in is equally likely. I may have gotten the scale factor wrong. Turns out if you make it so it's, I don't need to really normalize it here if I generate just kind of standard Gaussians. But I've normalized it here. But then I'm going to do one other thing. Turns out I need to scale it based on d divided by square root k. I need to put this factor in front here as well. And I'll come back and explain why that's there. So this is a scalar, the vector, and a scalar, right? So the hard part was getting this uniform, this vector that's randomly points in any direction u, and then I normalize it and I scale it a bit, and that's vi. Yeah.
Multiplying or subtracting?
Multiplying. Yeah, so I'm just putting them next to each other. It's not a dot product, it's a scalar. So this is a scalar and this is a vector quantity, so I couldn't subtract. Yeah. Okay, and then if you remember this projection, then now mu I of A is simply defined as the dot product between AI and VI. Right, so if you remember, this is Aij times Vij, right? If you just are coming at this fresh and forgot what the Euclidean dot product is, that's what it is, right? So this is a projection onto the direction spanned by VI, and this tells me how far along to go, right? If this was a unit vector, if you remember, if VI was a unit vector, and AI was here, right? So this was, remember, I'm in some high dimensional space. Then what this is doing for me is I'm projecting down onto VI, and I'm recording this distance. This inner product is AI, looks like this. This is true, it's this distance if it's a unit vector. I've scaled it up by square root d over square root k. So d was the old dimension, k is the new one, which is hopefully a lot smaller. So I've increased the norm of it a lot. Okay, so I've done that because whenever I do a projection onto another space, this was the origin before, so the distance from the origin is shrinking. And it tends to shrink a lot. Right? If I look at the squared distance, if I look at the squared distance from the origin, the square of the norm of the 2 norm of this point, then if I just look at the coordinate axes, it's the sum of the square of each of the coordinates. Right? And I'm essentially picking one of the coordinates at random. Now, I've not picked one of the original axes, I picked some other direction, but imagine I picked one of these original coordinate axes, it'd be roughly 1 over d of the total squared norm that I picked. Right? Now I'm doing this k times, so this is going to be 1/8 of the total squared norm, but I need to scale it up by d. Now this is for the norm, so if I square this, I get the squared norm. So the squared norm I'm scaling up by d over k, and I'm doing this k times, so I'm getting back up the effect of the full d original dimensions. Yeah.
Is that normalizing is what causing the vector to be always in the first quadrant, the direction?
The first what
The
direction?
vector's direction to be in the first quadrant? Because if it's in a different quadrant, you'd have a greater distance, right?
No, so it's not always going to be in the first quadrant. And so if I drew, I could have chosen the vector to be like this. This could have been vi prime. And now if I project, right, vi can come this way too, right? So it comes back, yeah, first right here, come back down here. So the projection now looks like this. Right? It could have also wound up, now I'm going back and forth, it could have also wound up over here, and it could have projected this way out of this port.
But either way, it's going to be closer.
Yeah, so it'll always be closer to the origin. Right? So if I just get the distance from the origin of every point, by doing this scaling, it keeps the squared norm to be roughly the right size. Okay, and this is the whole algorithm, right? I picked this d-dimensional Gaussian at random using this box Mueller transform we talked about earlier in the semester. I scale it a little bit. I really don't need to this normalization, but it makes it easier to see what's going on. It should be about the right normalization already. And then I just take the dot product. This gives me 1 coordinate. I do this k times independently, and I get k coordinates, and I'm done. Right, now this part of it, where each coordinate is a dot product, recall, is not too different from what PCA was doing, right? I got k coordinates as dot products with the right singular vectors. And these were chosen in some optimization kind of way baked inside of this singular value decomposition. So this procedure of it is the same, but instead of picking these V1, V2, Vk in some very structured way, I've just done this at random. And this basically works well, and it's giving different guarantees. Yeah.
So you only make k of these random vectors, and then you use the same k random vectors for every k?
That's right.
Okay.
I define the mapping once, and then for all the data points, I do this mapping. It turns out, and the reason why I wanted to think of A as a D by N matrix is now I can get a matrix B. I want to get a matrix B, which is N by K. Okay, and then I can do this by creating a, if I do this right, this is should be K by D matrix S. And each Sij, if I make this a Gaussian random variable, or just a normal random variable, each element of this matrix, and I do each of these independently, then this works. I can just fill up this matrix S with these Gaussian random variables, and this does the dimensional reduction in this linear algebraic way. Once people realized this, they said, well, what else can we put in place of S there? Right? It turns out you can also do Sij equals uniform between 0, -1, and +1. So I can fill up this matrix J where I pick randomly 0, -1, or +1. I can actually pick 0 2/3 of the time, minus 1 1/6 of the time, and plus 1 1/6 of the time, and I get basically the same guarantees. Right? Each of, and so this S matrix is describing this map. Each of the rows describes one of these projection maps, and there are k of them. Each give me a different new dimension. And then there's a cooler form where I have, if this is S and I look at any column, so before every row was one of these maps, right? So this was, mu I was a row here. If I look at a column, I can make these columns all zeros except 1, 1 at random. Right, so each column is all zeros, but I enforce there's exactly one value in one of the rows. And this actually works like this count min sketch that we talked about earlier. And this gives fairly similar guarantees as well. This one works a little bit worse, but if your data is very sparse, like it's mainly zeros to start with, so you don't like a big recommendation matrix, then this works much faster. In practice, they work fairly similarly. This maybe works just, maybe 5% worse than that, but it's much faster to implement on big sparse data. Okay, so let me just tell you that this does not work as well as PCA in practice for most applications. This is much slower. So I would say just as a user guide, use when D is, say, greater or equal to 100,000 and K greater or equal to 500, probably greater than 1,000. So with PCA and stuff, it was great for projecting down to 2 or 3 dimensions. That actually made sense. This really needs this randomness properties to kind of kick in, right? So I need K to be like 500 dimensions for this to be worthwhile. Sometimes you can go a little bit less. Typically, you might need 1,000 dimensions. There's been some stuff we've observed. And so then you maybe, if you want to do it, you might want to start this to be 10,000 or maybe 100,000 to do it. So if you have these really enormous data sets, really, really high dimensions, then this is pretty cool. Let me tone this down. Let's say 10,000. So you can go to 10,000 to 500. That's about the smallest scale where this really becomes useful. But if you get beyond that, and there are some machine learning data sets that are like this, these sort of techniques become useful, because then you spend a lot more time dealing with this 500 dimensional data, and you pay every time you have to read one of the dimensions. Okay, so there's a few other properties you can maintain from this, such as it preserves from regression properties and stuff like that. But I'll stop here. We'll talk a bit more about fast large-scale dimensional reduction on Wednesday. Quick question?
Okay, last question. So intuitively, can we think of each random projection as like kind of a weight between the original D dimensions that we're picking from?
Yes, it's randomly weighting.
Okay.
Yeah.
It's randomly weighting them, but the distance is scaled in accordance.
Yeah, I have to scale it back up, otherwise I'm shrinking by a factor of K over D. Right, I want to scale that back up again. Okay, so for the rest of the class period, we're going to break into groups. I guess you have a little bit less. You have about 12 minutes per group, and so these are your group numbers. Hopefully, you know what your group numbers are. Does anyone not know what their group number is? Okay, I'll try and figure this out. These are your group numbers. So okay, so this. Just to try and help you organize a little bit, if you're in these groups, why don't you try and make your way over to this side of the classroom, and kind of the higher groups towards the back, these towards the front, these kind of in the middle, and these on this side of the classroom. Yeah.